তেখেত লগ আউট হৈ গৈছে নেকি?
কিবা এটা এই হাৰিটো হৈছিল যে মানে লাইভৰ হাৰিটো আহিছিলে ঠিক আছে বাৰু উজ্জ্বল দা আৰম্ভ কৰিব পাৰো নেকি তেখেতৰ দুআষাৰ হয়তো পিছত মাজতো ক'ব পাৰিব হৈ যোৱাৰ পিছত কোৱেশ্চন আনসাৰ সেশনৰ মাজত
ঠিকে আছে
হয়
ঠিক আছে মই তেতিয়াহলে আৰম্ভ কৰিছো প্ৰথমতেই দুখাৰমান কথা কৈ লওঁ প্ৰথম কথা হ'ল যে আজি খুব ভাল লাগিছে কাৰণ সাধাৰণতে আমি যেতিয়া এনেকে টক দিওঁ সাধাৰণতে আমাৰ PhD ষ্টুডেন্ট থাকে নহলে বেলেগ সাইন্টিষ্ট থাকে আজি বহুত দিনৰ মূৰত এনেকুৱা সিচুৱেশন এটা হৈছে মানে যে মানে সৰু ভাইটি ভণ্টি বুলিয়ে কম যে তোমালোকৰ লগত কথা পাতিবলৈ এটা চান্স পাইছো আৰু আমি কিনো কৰো আমাৰ কামবিলাক কেনেকুৱা এটা ক'বলৈ চান্স পাইছো এইটো খুব ভাল লাগিছে আৰু দ্বিতীয় কথাটো হ'ল যে স্পেশালি আজি অসমীয়া ষ্টুডেন্টৰ লগত ইন্টাৰেক্ট কৰিবলৈ চান্স পাইছো এইটো মানে মোৰ কাৰণে বহুত গৌৰৱৰ কথা আৰু মানে খুব ভাল লগা কথা মনত পৰিছে আজি যে কিমান অলমোষ্ট 27 বছৰ আগতে 28 বছৰ আগতে আমিও তোমালোকৰ নিচিনাই ষ্টুডেন্ট আছিলো তেতিয়া কেতিয়াবা ভাবিছিলো সাইন্টিষ্টনো কি হয় সাইন্টিষ্টনো কি কৰে আৰু তোমালোকৰ চাগে তেনেকুৱা বহুত ভাৱ আছে হোপফুলি আজি মই তাৰে কিছুমান বস্তু ডিসকাস কৰিব পাৰিম তাৰপিছত থাৰ্ড কথাটো হ'ল অলপ টেনশনো হৈছে দেই তাৰ কাৰণটো দুটা প্ৰথম কাৰণটো হ'ল মই দেখিলো যে অসমীয়াতে কথাখিনি কোৱা হৈছে এটা মোৰ অসমীয়া কথাবিলাক অলপ মানে পিওৰ হৈ থকা নাই 27 বছৰ হ'ল অসমীয়া কিন্তু আনফৰচুনেটলি সববিলাক ভাষা ল্যাঙ্গুৱেজ বিলাক মানে মিক্স হৈ গৈছে কোনো কথা নাই তথাপিতো মই চেষ্টা কৰিম যাতে মানে অসমীয়া আৰু মেইনলি মই ইংলিছতে কম কথাবিলাক আৰু মাজে মাজে অসমীয়াটো কৈ যাম যদি পাৰো আৰু তাৰ পিছত আৰু টেনশন হৈছে যে যেতিয়া মনত পৰে তোমালোকৰ বয়সৰ কথা আমি খুব টান কোৱেশ্চন সুধিবলৈ চেষ্টা কৰিছিলো এনেকুৱা কোৱেশ্চন সুধি ভাল লাগিছিলে যাতে মানে ছাৰে আনসাৰ দিব নোৱাৰে I am sure তোমালোকৰ মাজতো তেনেকুৱা বহুত ষ্টুডেন্ট থাকিব মই চাওঁ তোমালোকৰ কি কোৱেশ্চন আছে মই আনসাৰ দিবলৈ চেষ্টা কৰিম but I'll be very happy if you ask me tough questions and খুব সম্ভৱ মই যিমান দূৰ পাৰো মই আনসাৰ কৰিবলৈ চেষ্টা কৰিম আৰু also my greetings to all teachers madams and sirs and so আজি মই basically talk to ekdom informally মই prepare কৰিছো and so let me start in English and I'll also keep falling back to Assamese language wherever I think it is appropriate. So I'll share my slides. Okay, I think now it is visible. It is full screen. Please let me know if it is not. So
yes.
Okay, thank you. So I am going to talk about chemistry with waste plastic, pollution remediation, oxygen harvesting, and solar energy utilization. So my chemistry kotha discuss korim waste plastic loi pelai aru ebilak bostu keneke important other chemicals hole nanomaterials hole convert koribo pari aru how we can utilize them, that is what I am going to discuss. So this topic is mainly related to chemistry, but I'm sure that there in the audience there are people from other backgrounds also, from biology and physics. But these materials that I am going to discuss is also interesting from, from physics as well as biology point of view as well. So before that, let me just introduce to you my institution. I am from IISER Mohali. IISER means Indian Institute of Science, Education and Research, Mohali. So Mohali is a city in Punjab. So Mohali is actually Mohali and Chandigarh. They are very close by. In fact, Chandigarh, Mohali, you cannot distinguish. For all practical purposes, it is the same city, except that the administration is different. So it's a very beautiful city, and I hope some of you will visit us. So this is the main campus. You can see here IISER Mohali is written. When you come from airport, this is the first thing that you will see. Then I show you the library, and we have very beautiful hostels. Our campus is very beautiful. Chandigarh is called City Beautiful. And we have very nice classrooms, big classrooms. And I show this to you because, we get very few students from Assam. Just hatot likhibo para. Just kejonman student ahe. As a TI student ahe, I try to help them as much as possible. So I request you that please, apply and get admission. We have a bachelor's degree, we have master's degree. You have to give JEE exam or JEE advance, or we also have our own examination. And then you can also come for master's plus PhD, and you can also come for PhD program. So please take this opportunity, and I invite all the people in Assam to take this opportunity. So the key points in today's talk is, I'll give a very brief introduction to nanomaterials, maybe 5-10 minutes, and I'll discuss some contemporary, social problems, but main focus is how we can use chemistry or say nanomaterials to provide solutions to some of the burning problems. And this will involve, specifically conversion of plastic to nanomaterials and some of the novel properties that we have discovered in our laboratory. So what is nanoscience? So nanoscience, a nanometer is 1 billionth of a meter, okay, 10 to the power minus 9 meter. So the nanoscience is the study of plastic particles that have size of about 1 to 100 nanometers. So nanoscience itself can be physics, chemistry, biology, or anything else, engineering, okay? It is the size which matters. It has to be something like 1 to 100 nanometers. It depends on the properties. It depends on the application, specific application, but very small. Molecules are something like, some of the molecules are about 1 nanometer. Our DNAs are, say, DNA, RNA, molecular systems. They are something like a few tens of nanometers. Cell, our body cells are micrometer size, so they are smaller than even cells. So this is the size domain that we are talking about. I can give you one more example. See this slide, I'm speaking for about, say, 30 seconds, and if you calculate in 30 seconds to 1 minute, your fingernail knock or your hair was fully to 1 minute almost 1 nanometer grow. So that is the that is the size that we are talking about. So we know Bohr radius, all our students, we know Bohr radius is 0.5 Armstrong. And carbon atom is 0.17 nanometer, because carbon-carbon bond is 0.334 nanometer, right? All of us know carbon-carbon bond is 0.34 nanometer. It has 2 carbon atoms, so half of it. Okay, radius of carbon atom is 0.17 nanometer. So if we take 1 nanometer, you will have about 3 carbon atoms. Okay, now if we have a box, 1 nanometer box, okay, we are talking about 27 carbon atoms, about 25 to 30 carbon atoms will be there. So we are talking about that many number of atoms. And say if you take a box which is about 100 nanometer in size, okay, a cubic box. So we are talking about, say, 10 to the power 7 carbon atoms. So we are talking about 10 to 10 to the power 7, okay, 10 into 10 to the power 7, so 1 to 10. But this many number of carbon atoms roughly define nanomaterials. So if you want to compare this with something that we know about Avogadro's number, right? 1 mole, Avogadro's number. So Avogadro's number is something like 10 to the power 23 atoms. So a nanomaterials is actually much smaller than Avogadro's number. So that is the take-home message. Now, when we have nanosystem, it contains hundreds to about, say, 1 lakh atoms. Okay, there are 2 things are very important. Okay, why nanomaterials are special? When you compare to, we all of us know atoms, we all of us know molecules, right? And we also know the materials which we encounter day to day in day-to-day life. Now, these nanomaterials, they are special and they are different from molecules as well as the conventional materials that we see because of 2 very important things. One is their electronic properties. Okay, so this property changes in this size domain. The second very important thing is their surface area. And we'll see in a minute what does it mean. So first, let us discuss about electronic properties. Right? So we discussed that if we have about 1 nanometer, okay, in 1 nanometer, you have about 3 to 4 carbon atoms. Okay, let's say 3 to 4 atoms. So it is bigger than an atom. When we talk about nanomaterials, it is bigger than an atom, but it is much smaller than the conventional solids. Now, all of you remember the molecular orbital theory, right? When 2 atoms combine and they form molecules, okay? So the number of electronic states increases. If you have 2 atoms, for example, 2 hydrogen atoms, each of them has 1s orbitals, and they will, when they combine, they form bonding and anti-bonding orbitals. So it becomes 2. Okay, initially they had only 1. A hydrogen molecule have 2 states. So similarly, if we increase the number of atoms, the number of energy levels keep increasing. And it keeps increasing. After some time, what happens that it increases so much. Okay, it becomes 10 to the power 23. You cannot distinguish them anymore because they are very close to each other. Okay, even room temperature is enough. Room temperature is a measure of some kind of energy, right? Because room temperature, many things happen. So room temperature is enough. You cannot distinguish between these states. So they become like a band, like a rock band. So they become like, these are called energy levels or bands. Okay, energy bands. So these nanomaterials are in between molecules or atoms versus these bands. I'll show you one experiment now. See, all of us know, for example, methane molecule, right? So methane molecule, see, let's forget about what this experiment is, precisely, but let us just focus on the fact that carbon has 2 p orbitals, right? We know carbon has 2 p orbitals. So, and 2 s orbitals. Now, in this measurement, I can see this is called XPS spectroscopy, X-ray photoelectron spectroscopy. So I can see the 2s energy and 2p energy. You see, if you look at the x-axis, this is the energy, electron volt, this is the energy scale. Now you can say one 2s and one 2p. You can see two peaks, right? Now when you have ethane, okay, now this 2s has split into two because it has four molecular orbitals, and this has also split into two. So this is what we have read in the textbooks. Now you can see in the experiments, okay, it has become 2. And this gap between 2s and 2p, okay, you can see this is the gap. If you look at my cursor, this gap has decreased here. Now if you keep going further, this is propane, this is butane, and number of N is increasing. You see, accordingly, the number of states are also increasing, and this you can experimentally see. The other thing is that the gap between 2s and 2p is always decreasing. It is becoming smaller and smaller and smaller. And this is something like here you can see like two skyscrapers, tall buildings. But if you see, this is basically the same thing again. This is the binding. If you turn it 90 degree, if you just turn it 90 degree, it will start looking like molecular orbital. You can see there are 2 orbitals, and then it becomes 4 orbitals. It becomes, and this number of orbitals like this, it increases. Okay, so what I'm trying to convey is that when you increase the number of atoms, it bends, okay, the energy level changes. And that is why it is very important, why it is different from molecules as well as bulk. If you remember bulk, we discussed it cannot change anymore because all these are completely crowded. Even if there is change, virtually there is no change because they are already crowded. But before that and after the molecules, you can see variations, and this is the reason that we call them, nanomaterials. Now let me ask you this question, okay? And can the same material have different colors? It's a very simple question, but also a very difficult question. See, whenever we talk about materials having different colors, what we mean is that it must have some different chemicals in it. But the question I'm asking is that the material is same, but the color is different. Is this possible? And I'll show you one example. So here you can see these are cadmium selenide, okay, CDSE, and these are all are CDSE, but they have different colors, okay. And so it is possible because if you remember the previous slide, I showed that this energy gap changes and the color appears in a material because of electronic transitions when light falls. Now, because these energy levels are changing, the excitation is also changing. So the light, actually the material absorbs also changes, and that's why this color change you can see. So the answer to this question is yes, the color can change even for the same material. Right. So that is the first example, that is electronic properties, okay, or chemical properties, you can say. The other very important thing is surface area. Let us look at this example. Okay, let us look at this box. Okay, this box is 1 meter. Okay, you can see this yellow box, 1 meter. So each surface has a surface area of 1 meter square, and it has 6 surfaces, right? 1, 2, 3, 4, 5, 6. So that means total surface area is 6 meters square. Now you take this box and you cut into half in all sides. Now you see, you will end up getting 1, 2, 3, 4, 5, 6, 7, 8 boxes. Now you calculate the surface area. Now each one has a surface area of half meter square. Okay, half meter square into 6. Okay, is the surface area of one box multiplied by 8. So 12 meters square. Okay, see the same material. Now when you make it smaller, the surface area increases. If you cut it into 1/3, it becomes 18 meters squares. So when you make the material small and small, the surface area increases. Now let us actually go to the nanoscale regime. This we discuss in meters. Let us say we have a spherical nanoparticle, okay, about say 12 nanometer. Okay, so this will have about say 5 lakh atoms, and the surface will have about 50,000 atoms. So roughly 10% atom is on the surface. On the other hand, if you make it further smaller, if you go to 5 nanometer, you see, then about 30,000 atoms are, there will be total 30,000 atoms, and about 8,000 atoms are in the surface. So 25%. So when you make this particle smaller, its surface area increases. The number of atoms on the surface increases enormously. Okay. In comparison, if you talk about a marble, for example, the number of atoms on the surface will be something like 0.000001% or even smaller than that. So the question is why it is important in chemistry, because one of the most important contribution of chemistry to humankind is catalysis. And catalysis, in most of the catalysis, industrial catalysis, solids are used. Okay, these are called heterogeneous catalysts. When we are using solids as a catalyst, the reaction happens on the surface. Now you can correlate with this, that when we have large number of surface atoms, so you need very little amount of catalyst. Okay, so this is very good because it is sustainable. Okay, it is energy saving, it is money saving, and it can make the process more efficient. So this is all very important for catalysis, and many other also for many other reasons as well. So, and this last few years, nanomaterials has been widely used in catalysis. Okay, as I discussed, these are called heterogeneous catalysis because most of the reactions happens in solution. Okay, but these catalysts are actually nanomaterials. They do not dissolve in solutions because they are actually solids, very small solids. So it is called heterogeneous catalysis. The catalyst is solid, but the reactants are liquids. So there are two important things, important catalysis reactions that I'd like to mention. The importance of nanomaterials in this case is energy efficiency, energy harvesting, and environmental remediation. So let us see what it is. It is used in drug synthesis. Okay, these surface atoms are highly energetic. Okay, because they are uncoordinated. If you take an atom inside the nanoparticle, it is surrounded by similar atoms. But if you take an atom on the surface, it is uncoordinated. So it is highly reactive. So it improves the catalytic efficiency of a reaction. In case of energy harvesting, it is, I think all of you are aware that hydrogen energy is becoming very important. And even Indian government is pushing for green hydrogen and blue hydrogen energies. Okay, so it is used in hydrogen energy. It is used in photocatalysis, something like photosynthesis. And very recently, people are trying to make ammonia from nitrogen. Is extremely important reaction. We have nitrogen, plenty of nitrogen in air. If we can convert it to ammonia, we can make urea, and then we can make fertilizer. Okay, urea is the single most important chemical for feeding us. So even now we use more than 100-year-old technology, Haber's process, to make ammonia. So this is very recently people are trying to do this. So environmental remediation. For example, pollutant degradation. Okay, pollution is a big problem, all of us know. CO2 removal from air. So I'll not be discussing these things, but I just want to show you the scope of using nanomaterials and doing research with it. Is that very, very important, and burning problems can be addressed by using nanomaterials. So this is my just two more slides. to tell you that energy research is very important. All of us know, right, that if we don't have electricity, so we become like poor countries. So energy is very, very important. And we are having problems with energy nowadays for two reasons. One is that we get energy from fuels, fossil fuels, coal, which gives a lot of pollution. And also, they will end at some point of time. So we need to use renewable energies. We need to use sunlight directly or wind energy directly. So there has been a lot of effort all over the world to use sunlight to generate energy. And this is particularly important for countries like India. And so you know that government is pushing for solar cells. Okay, it is green, energy efficient, but we need to make it even better. So this is a burning problem I'm talking about. And the other is also, pollution. Okay? India is one of the worst affected countries by pollution. So we need to get rid of pollution. So we need to get rid of fossil fuels. We need to get rid of CO2 and other pollutants from the air, in which nanomaterials are very important. So this is all about my introduction. Now I'll come to something very specific that we're going to discuss today. How to utilize waste plastic. Waste plastic is also a menace. It has created hell everywhere. You cannot burn it, you cannot dump it, nothing happens to it. We keep generating it and it just remains there. It never degrades. So in my talk today, I am going to explain how probably we can utilize waste plastic to make nanostructures, and then something new, something that you may have never heard of. I'm going to discuss something called graphene carbon quantum dots. Okay. So essentially, it will mean first I'll discuss how waste plastic can be converted to carbon quantum dots, and then I'm going to explain something very, very new, that is graphene quantum dots. How carbon dots can take, graphene means can take oxygen, or it can give oxygen, release oxygen. Next, I'm going to discuss how I can use carbon dots to harvest, this infinite amount of solar energy and do some chemical reactions. Okay. Then something I'm going to discuss called something which is introduced from our laboratory called carbon dot autophagy. Okay, that means these materials, okay, they are very efficient workers. Okay? They can do some chemical reactions very fast, but once the job is done, they kill themselves. Okay, you don't have to worry about it. It will do its job and it will go away. Okay, it will disintegrate. And the last property that I'll discuss is called, again, a very new property that we have introduced, is called carbon dot hypoxia. Okay, what it means is that we can control the amount of oxygen levels on carbon dot. Okay, that is too technical, but I can, if you look at this picture, I show you a picture of a teacup having some red tea, ficasa. Now, if I ask you, see this is water. So essentially, it has some oxygen. Water always have dissolved oxygen. Now, if I ask you this question, if you are having tea in the evening, what kind of oxygen level you have inside this beaker? So you may not know the answer, but so if somebody tells you, you will know that this much amount of oxygen is there. Now, if I ask you the same question, but I tell you that now you are not sitting inside your house in the evening, but you are sitting during daytime, a sunny day, you are sitting in the sun, a bright sunlight. Now, what is the level of oxygen? Now, the answer is, you do not know the answer. Nobody knows the answer actually. So what we recently figured out is that in this teacup, the oxygen level is different from when you are inside the room. Point number two is that the oxygen on top is different from oxygen at the bottom. And I'll explain you why. It is something very simple. But this is something also very, very new, which we call it hypoxia. Okay. Hypoxia normally means in hemoglobin in blood, when you have less amount of oxygen, it's called hypoxia. So for the students, again, some key questions. Can a material breathe? Okay. That means, can it uptake and release oxygen like hemoglobin does? And I'll show that the answer is yes. See, you can see a plot here. Okay. Do not bother about the plot. Only what you see is that on the y-axis, you have oxygen, and the x-axis, you have time. So at this moment, you can see that only oxygen level is coming down, again going up, coming down and going up. So it is something like breathing. The second question that I'll address is that, can we actually use waste plastic for harvesting limitless solar energy? And see, I'm going to show that you can see in this picture, there's some plastic on my left-hand side, and this, after some chemical transformations, convert to this red powder, which is essentially carbon dot. And because it is colored, that means it is already absorbing light. Absorbing light means harvesting light. Now only question is how we can utilize it, and we'll see how this can be utilized. So both these things, now I will also show you, I'll combine these two. First, you take oxygen from air. Okay, so you are taking oxygen for free because it is coming from air. It can breathe, it can take oxygen. Then it can also take light. So if I combine these two, light is energy, right? Light is so I can do some oxidation reactions. I can use the same oxygen, I can take sunlight, I can do some oxidation. And this is very important because oxidation reactions, for those chemistry students, you know that you have to use something like H2O2, K1O4, and K2Cr2O7. These are not good, these are toxic. Once you do a reaction, you have to throw it somewhere, or you have to treat it. Okay. Now, how about if you simply use free air and do the same experiment, same reaction without using this? So I'll show that this is possible to do because of this breathing properties. The another key question is something. Now let me tell you a part of history. Photocatalysis, heterogeneous photocatalysis started about 53 years back. Okay, it started in Japan, and when it started, one of the dream was the following: that this is a canal. You can see some red color is there. This is some kind of pollutant from textile industry. So, and it is very difficult to clean it because there's a lot of water. You cannot secondary to uneven, and you don't know how to treat it. Okay, you have to do some chemical treatment or something like this. So when photocatalysis was discovered, it was hypothesized that if you put some photocatalyst here, okay, photocatalyst means it will act with light. When light falls into it, this catalyst will degrade it and it will make the water clean. So this was a fantastic idea and this was a dream, but there was a problem. And the problem was that if you put a photocatalyst here, then you cannot remove the photocatalyst. Either it will fall down, it itself will become a pollutant. So last 50 years research, still this cannot be implemented. So I just wanted to show you that we discussed about carbon dot autophagy. Now autophagy is something, you see, this is a carbon dot solution, and if you keep it in air, if it is getting used, if the carbon dot is getting used, it carbon dot kaam kori ase, it is perfect, it is working, it is healthy. As it kaam kora bon kori diye, okay, when the job is done, it kills itself. Okay, so this is the difference. Is initially it used to attack the pollutants. It was attacking the pollutants and killing them. Now it kills itself because it has a lot of energy. Okay, since all pollutants are gone, it can kill itself. So that is something we have figured out. This is the first material which shows this property. He calm হৈ যোৱাৰ পিছত ই নিজকে নিজে মাৰি দিয়ে. All right. So so I'm going to discuss about photocatalyst because we want to use sunlight. So photocatalyst has two parts. The one part is the photo, that is the catalyst. All of you know what is catalyst. Catalyst is something which improves the rate of the reaction. Okay. And photo is what? Photo is just light. Okay. Normal reaction like we just give some temperature, we heat it up. So in this case, we do not heat it up, we just give light. Light is the source of energy. Okay. So one of the example is, for example, natural photosynthesis. Okay. So in natural photosynthesis, carbon dioxide and water combine to give you glucose and oxygen, right? So this is an example of photocatalysis, and something similar can also be done in laboratory, provided we have efficient photocatalysts. Now, lastly, let me also tell you about carbon dots. So mine is photocatalysis, carbon dot, and waste plastic, right? Now, what is carbon dot? Carbon dot is a nanomaterial. Fine. It looks like this. Haldi pani nishna lage. It's like, or something like, it's very beautiful color, and it is otherwise like Picasa. And then, if you look at this, okay, it was discovered in 2004. Accidentally, it was discovered, and it has a few nanometer carbon particles with surface functionality. It's a very cheap material. Okay, carbon is something very, very cheap. In fact, when you burn, if you cook in a carbon dots get produced. But if you are taking tandoori chicken, okay, tandoori chicken normally will have some amount of carbon dot. Or if you burn candle, the candle it will have some carbon dots. So carbon dot is something like this. All of us know graphite. So a single piece of graphite is called graphene. Okay, you can see the hexagonal sheets. And if you just take a very small pieces of graphene, and if you put it on top of that, one on top of the other, you get what is called a carbon dot. It's called dot because it is very small. So if you want to look at the picture, it will look like this. You can see these are like dots. It's something like about 5 to 10 nanometer size. Okay, they are like dots. And maybe this is for our teachers. Maybe I should not have put it here anyway. I put it, so I'm going to tell it. Carbon is something very important in human history, and even if you see just last 20-30 years, carbon dot is very important. If you look at different carbon structures, carbon nanotube, okay, carbon nanotube, and something called fullerene, something called graphene. So three things I told: graphene, carbon nanotube, fullerene. And the fourth thing I am telling is the carbon dots. Now graphene has already got Nobel Prize. Fullerene got also Nobel Prize. Carbon nanotube is fantastic, but it has not got Nobel Prize because it's very difficult to find out who actually discovered it. But in terms of importance, carbon nanotube is also very important. So the question is, how about carbon dots? Can they also be something very, very important? Can we find something completely new that no other material can show? That was the question. And finally, I'm not going to explain this. All of us know that plastic is really bad. And there are lots of research going on how to convert plastic to something useful. So So I'll show you the synthesis of carbon dots. Now, some of you might know graphene, which got Nobel Prize a few years back, is actually, after that, the synthesis of graphene has become very important. The guy who got Nobel Prize actually just took some graphite, okay? That means your pencil, okay? And if you put a Scotch tape, okay? Just a cellotape, and if you put it on top of the pencil, and if you pull it apart, you will have some graphene pieces, okay? The small pieces of carbon will come out, that will be basically graphene pieces, and that got Nobel Prize. By the way, after that, chemists worked on it, and they have developed a process to make large quantities of graphene, okay? But they are slightly oxidized, okay? Because so they are called graphene oxides, okay? It will have some OH groups and COH groups on carbon. So there is a standard technique to make graphite, okay? You take some pencil or you take some graphite powder and you put just H2SO4, sulfuric acid, and KMNO4, and then H2O2. Then you will get graphite oxide. Now, our process is something similar. We'll just come back to this. So what we did is that, this reaction is known for a long time. This is an alkene chain, you can see. This is polyethylene, okay? This is a branch, but polyethylene, this R is H, okay? Now, if you treat it with H2SO4, okay, sulfuric acid, it is, so it will, it will remove, it will introduce, so this H2SO4 breaks to H2O and SO3. This SO3 attacks this carbon bond, okay, and this compound forms, okay, this backbone, the SO3S gets attached to it. Now, further, it reacts further, and then this double bond gets introduced. We'll not go into the reaction mechanism. So what I'm trying to show that this is all are single bonds. Now you see one double bond forms, okay, and then this process continues, and there are basically many double bond forms, okay? So many double bond forms. So we started with a single bond, and we have all double bonds, alternate double bonds, potentially alternate. Sometimes it's not so ordered, but there will be many double bonds. Now, if we have many double bonds, if we can make a cycle, okay, these double bonds will form something like benzene. So, but we have to do many experiments to prove it, but we could do this. And so it forms graphene. So this is a small piece of graphene, okay? If you extend it a little bit, here you can say this forms graphene. But as I told you, this is not a perfect, all single, they are not exactly, alternate, okay? This is a rough process. This happens at very high temperature. High temperature means something like 100 degrees, and very strong H2SO4, highly concentrated. So it is not perfect. So some parts are actually only single bonds, okay? It cannot cyclize. Now, if you put some H2O2, these bonds oxidize further. This can oxidize. Graphene is very stable, it doesn't oxidize. So these can oxidize. So graphene, this particle, it falls off from big plastics. Okay, these pieces will fall off, and that is how we have been able to make carbon dots. Okay, so this is the first report of how carbon dots can be prepared from waste plastic. So I can see the different stages. This is actually a plastic bag which we picked up from dustbin, and then you can see when you put H2SO4, it becomes carbon, it becomes graphene. Okay, and then when you put H2SO4, it forms these dots, and these dots are soluble in water. So you can see this beautiful color. This solution is stable for several years. It remains there. Okay, but you can remove it from there and you get these carbon dot particles in large quantities. And I showed you that this is about, say, 5 to 8 nanometers in size. And if you look at carefully, okay, in high resolution microscopy, you can see the graphite sheets here. Okay, the graphene sheets can be seen here. So we confirm that this is actually carbon dot. I will skip the mechanism part, okay, because it might be slightly complex. So here you can see this is an absorption spectra. Okay, those of you who are aware of absorption, you can see that this absorbs light from about say 450 or 500 nanometer. So this is visible light. Okay, so it absorbs light, and this is what and you can see from the color itself, it absorbs light, and it also shows emission. All right. So coming back to the synthesis, why this synthesis is, see, carbon dot is not, we are not the one who has discovered or who have made carbon dots. There are thousands of, there are many reports where people know how to make carbon dots. But then the question is, what is special about it? Is it sustainable? So it's quite good actually. If you see, the yield is very high. Okay, this is the highest yield that you will know in the literature. And then it is crystalline. I showed you that graphene sheets. You can see those graphene layers. So this is crystalline. Normally, you will find carbon dots which are amorphous. Only 5 to 10% of the known carbon dots are actually crystalline. Others are amorphous. So then I will not get into more specifics why this synthesis is very good compared to what is known, but this is very easy to make. Okay, carbon dot is very easy to make, but it is very difficult to purify. So in this way, there are no impurities. It is extremely easy to purify. So in terms of sustainability, this is a remarkable improvement compared to what is known. So let's come to the first interesting part in terms of properties, oxygen harvesting. Okay. Now, oxygen harvesting is something very important because when you do oxidation reactions, and as we discuss, we make carbon dots to do some reactions. And when you specifically, if you want to do oxidation reactions, as we discuss, it's not good to use the conventional oxidizing agents. But why people cannot use air, free air, for doing oxidation reactions? One of the reasons is that oxygen solubility in water is very poor. Okay, and oxygen diffusion is also very poor. So if the oxygen gets used up, okay, then the next oxygen doesn't go to the catalyst. Okay, it takes long time to go, and it doesn't get stabilized. It becomes more complex. But one of the things is for sure, if you can put a lot of oxygen on a catalyst, the reaction will become fast. So we need a catalyst which can actually take a lot of oxygen. And such materials are, as far as I know, is rare, which can act as a catalyst also. At the same time, it can take a lot of oxygen also. I will not get into the details why it absorbs oxygen, but I'll show you here the main results. So again, these plots are confusing, so do not worry about the plot. You see, this is, if you look at this liquid, okay, yellow liquid, this is carbon dot. So it can, in this plot, I show that oxygen can, it can take oxygen and it can release oxygen. And you look at this from these numbers. So this on my left hand side, this is water, and right hand side, I have carbon dot solution. The only thing that you should see is these numbers. Okay, the same amount of water and in both, and about 0.1% carbon dot is added. Very small amount of pinch of carbon dot is added. Okay, now you see the amount of oxygen level increases from 300 to 600. The oxygen amount has become double. The second important point, you see, if you take water and if you, for example, put carbon dioxide into it or nitrogen into it, slowly oxygen will go if you keep putting nitrogen. Then you stop the flow of carbon dioxide or nitrogen. Then it will again take oxygen from air. Okay, So this process takes about, in this experiment, it takes about 10 minutes in water. Okay, and this takes only 4 minutes in carbon dioxide solution. So the oxygen diffusion has also become very fast. Okay, oxygen amount as well as oxygen diffusion has become very fast. So it is like this. If you have water and oxygen, so 300, forget about the unit, 300 has become 600. It's a huge jump. All right. And then you can calculate the amount of oxygen on carbon. And it is about, say, 1 weight percent. That means 100 carbon atoms will have, 200 carbon atoms will have 1 oxygen molecule, which is something similar to also hemoglobin. All right. So again, here I saw that, here you can see when you pass oxygen into it, okay, air into it, it goes down. Okay, then you just leave it, it again takes oxygen from air. It goes down, it again takes oxygen from air. So if you pass some gas, it will release oxygen and it will take it back. So this is not something, it is simple. Actually, anything, the same thing will happen if you take any material, but the amount is extremely high. Okay, the amount of oxygen that it can take and it can release is extremely high. So again, I will not explain this, but as I explained to you that it can increase the diffusion of oxygen, the diffusion coefficient of oxygen in water very fast, because the carbon dioxide will go to the surface of the water and catch a lot of oxygen and it will bring it down. So let us see now some applications. Okay. What happens? Say, one carbon dot. Okay, carbon dot is 5 nanometer or 8 nanometer. It takes about 100 plus oxygen molecules. Okay, it is sitting on top of it. Okay, now when they are colored, so it absorbs light. When carbon dot absorbs light, electrons get excited. That's why it absorbs light, right? So electrons get excited. These excited electrons is taken by the oxygen, and it forms a series of intermediates which are called ROS, or reactive oxygen species. It can form various reactive species. It's something like H2A2 or superoxide radical or OH dot or something like this. Okay, OH minus. So these are called ROS, and these are very reactive species. Okay. I should tell you a little bit of history. In this case, people are trying to use free air for oxidation reactions. But the only thing is that because oxygen solubility is less and diffusion is less, you have to use high pressure of oxygen, or you have to constantly flow oxygen into the reaction, which is again very, very expensive. And we'll come to this one. Now, one of the applications, I showed you this picture that we want to degrade these dyes. Okay, and you can see this is a colored dye. Okay, on the right hand side, this colored bottles, you can see this actually degrades this light. If you take pinch of carbon dioxide, it degrades and the color goes away. Okay, and this is the many catalysts known for this. As I told you, about say for 50 years, people have developed this kind of catalyst. But it is very interesting because it is very stable. See, people normally, this is 100 times, one catalyst has degraded such colored materials for 100 times. Okay, it is still very, very good compared to a standard material, something like TiO2. Okay, TiO2 is the first catalyst where this phenomenon was discovered. Okay, and this is very, very active. Right, and this degradation happens because of the ROS. Okay, it oxidizes this. These are some dye molecules. Okay, that's why you get colors. There are some organic molecules where you have conjugation. So this ROS, oxygen species, they oxidize these dyes to form CO2. Now, this is an uncontrolled reaction because everything breaks down, okay, and finally you get just CO2. Now let us look at some control experiments. So there are two specific reactions, amine oxidation or alcohol oxidation, okay. So these reactions are well known. Photocatalytic way is also well known, other ways is also well known. But what is important is that these reactions are always done using oxygen purging. Okay. Now, if you use these carbon dots, for example, you can see, if you look at this box, this is a reaction, do not matter. Only what you see is that some sunlight, okay? In sunlight, we do this reaction, and this is similar to the xenon lamp. So I am showing everything in xenon lamp. We can assume that this is actual sunlight in Mohali. Okay, this reaction is done in Mohali sunlight. Now, if you look at this yellow box, you see, if you look at oxygen and air, okay, one reaction is done in oxygen, one reaction is done in air. The efficiency is same. Okay, there is no compromise in the efficiency. In conventional catalysis, if you do this reaction in air, it is at least at least 3 to 4 times slower. So this is a remarkable improvement because of oxygen harvesting property. Further, if you do this reaction even in nitrogen, simply do it in nitrogen, the reaction never happens. But in this case, using carbon dot, it happens because it has oxygens. It doesn't release all the oxygens. So it is still reactive when you have nitrogen. Okay, and it is quite good compared to conventional catalysts. So this is a chart, again, very busy chart. You do not have to bother about it. In fact, please do not bother at all. The significance of this result is that we do not have to separate oxygen from air, which is an expensive process, if we can use carbon dots for industrial applications, large scale applications. Or this is a high pressure reactor, where oxygen reactor, and there's a possibility that we can, if you use carbon dots, we do not have to use this kind of reactors. We can use simple reactors, and you can use air. Right. So now, next thing I'm going to explain is something called autophagy. And as I explained, autophagy means killing itself. Okay. Our cells, constantly regenerate. It also means that the old cells die. The old skin peels off. They die. And so, in a similar way, what I'm going to say that these carbon dots, when they are being used, okay, they are working, they are doing catalysis, they are healthy, and nothing happens. But once the reaction is over, they kill themselves. Okay, and I explained this why this is important, because if you want to clean natural water bodies, and very hypothetically, if you have this carbon dots, which is very cheap, you make it from waste plastic. So only thing you use is H2SO4. This can be recycled. So the plastic goes to carbon dots, and you throw some carbon dots here in this river. So water will become clean. Ideally, water will become clean. But the problem remains that you have to recover the catalyst. Otherwise, the catalyst itself will become a pollutant. So we found something very interesting in the laboratory. We are doing this dye degradation reaction. You saw that color dyes. So by mistake, what happened? We are doing these cycles, and then between 10th and 11th cycles, first, second, third, fourth, up to 10th, the efficiency is more or less similar. But 10 to 11th, we kept the light for little longer time in carbon dots. After the dye is gone, okay, the dye is gone, we still kept it. Then the 11th cycle, the efficiency become less. Then we started looking into it, And you can see here, these solutions B1, B2, B3. This is carbon dot color. Okay, carbon dot color is slowly fading. Okay, this is called CQD bleaching. By the way, this is also known. This is well known. CQD bleaching is, everybody has seen that if you keep using carbon dots, their color slowly fades. And we looked into it, actually why it fades. And there are many hypotheses. Okay, certain things changes in the carbon dot. What people have never seen, that when the carbon dot is changing, color is changing, is there any gas evolution? So when we looked into it, and we figured out that actually CO2 forms. So this was a discovery. This was an accidental discovery. But then it is not, once we got it, it is not difficult to rationalize. Okay, it can be very easily understood because it has this ROS. Okay, so this ROS reacts with a reactant. Okay, when the reactants are there. But once the reactants are over, okay, but these ROS species, they remain there. Okay, so what they will do, they're excited, they are ready, they want to do something. So what it does is that it kills itself, it attacks itself. Okay, so this carbon dot has carbon, so it attacks those carbon molecules and forms CO2. And then once we realized it, actually we kept these carbon dots for a long time in sunlight. Normally these reactions are done for 3 hours, 4 hours. We just decided to let us keep it for a long time. And we figured out that if you keep it for 38 days, you see all the carbon dot is gone. But a similar solution, if you put it in dark, nothing happens. It all remains there. So, by the way, one important point here, this carbon dot has to be kept alone. If you keep it with some reactant, okay, the color of the solution doesn't change. It will remain same. So as far as we know, this is the first material to show such behavior. Okay, this means that no need to recover it. Okay, if you put it in a river, it will clean the reactant and slowly it will become carbon dioxide. It will, I understand that it will, carbon dioxide will form, but that is a delocalized problem. The concentration is less, it will dissipate in air. But locally, local pollutant, high concentration of pollutant can be treated using this, is what we propose. So the last thing I'd like to explain is something called light-induced hypoxia in aqueous carbon conductors. Okay, hypoxia is something again related to blood. So since we thought it is oxygen, we'll connect everything to blood only. Autophagy is related to again biological system. And then hypoxia is the low oxygen level in body at the tissue level. Okay. Now, why this is important? This is not just oxygen. If I tell you something, you do a photocatalytic reaction. We know what is photocatalytic reaction. Now, and we know the reaction rate depends on the concentration. All of us know the reaction rate depends on the concentration. Next question is, the next point is that we also know that in a catalyst, the reactions happens on the catalyst surface or active center, okay, near the catalyst. Now the third question, which nobody knows, is that if you are doing a catalytic reaction, if you are doing it in dark and if you are doing it in light, okay, does the concentration vary on the catalyst surface or near the catalyst active center? This question, as far as I know, nobody knows the answer. But then it is very important to know what happens to the reaction concentration when you put it in line, specifically in photocatalytic reactions. And the reason it is not known is because nobody knows how to measure it. Because the active center, there will be small amount of reactant, right? Rest will be in the solution swimming, rest molecules will be swimming, only few will be at the catalyst active center. and nobody knows how to measure that small amount, even how to catch the catalyst and look at it. So, all right, this is what I have already explained. And so what we found is that if you look at dark and if you look at light, these are two schematics. You will see very easily here we have many oxygen atoms, you can see. Okay, but when it is in light, it has fewer amount of oxygen atoms. And what we have found is that this process is reversible. If you put it in dark, it will again take oxygen. If you put it in dark, and if you put it in light, again it will release oxygen. And you can look at this, okay. So if you look at the saturated levels of oxygen, this is, the number is 520 in light, and in dark it is 650, okay. So you can see a drastic change in the level of oxygen. Well, you do not see the same, there is no change if you just take pure water, okay. Both the plots overlap, but here you see that it is different. And here you can see that this is actually a reversible process. Light, dark, light, dark, light, dark. So this keeps happening. So I'm not going to explain the reason why it happens, but very briefly, the decrease of O2 content in light is due to light-induced desorption of oxygen or sun absorption of O2. Okay, all right. So there was a confusion that how to explain this. Okay, let's take to this message that this process happens. Well, I am really not going to explain this. Only what I am going to tell is because it is slightly confusing and I need to explain for several minutes. So it's very simple to know. Okay, I got a simple way to tell you. So if you take these boxes and suppose one is closed, one is open. Okay. Now, if you put light, okay, in the closed box, okay, there is no change of oxygen inside here, inside this bottle, because the oxygen cannot escape. Instead, oxygen level remains same. But if it is an open vessel, you'll see the oxygen level goes down because oxygen escapes the air, right? Now, the second important point is again, it is just a summary that oxygen level in the top is more than oxygen level at the bottom. You see, because once it releases oxygen, it takes more time for oxygen to go to the bottom. Okay, so that's why if you put from the top, so from in the top, the oxygen level is more, and here it is less. So this also means that if you put the light from the top and light from the bottom, you have different amount of oxygen. You can control the amount of oxygen inside the beaker. Now, second point is, you see, the amount of oxygen it releases depends on the wavelength of light, okay, because it absorbs only, see, this is the absorption spectra, okay, and it absorbs only after 500 nanometer. Okay, that means if you shine it with 550 nanometer light, there is no hypoxia because the carbon dot itself doesn't absorb light. Okay, so there is no light effect. Only where it absorbs light, you can see this effect. So I think this is my last slide, or penultimate slide, but I'll briefly explain the origin of this. Why light, in light this oxygen releases? It is simply because when these carbon dots get excited, this excited electron, that carbon dot behaves like a charged particle, okay, and because it has charged particle, it repels the oxygen molecules, and that is why the oxygen molecules goes away. So there are details, theoretical calculations, but we are not going to discuss this today. So this is the final slide. This is something maybe I should end with a story. So the story is that so we're submitting this paper to many journals, and they were not accepting it. So one journal in particular, they're very upset. They did not accept our paper many times. So one night I was about to sleep. It's about say 2:30 at night. So we sent the paper, and then the journal said that no, this is not a very important work. We do not want to publish. So we requested them several times. They were very upset still. They still insisted this is not important. So my family was sleeping, and I have a small kid. He has these colored pencils. So I took a piece of paper and I have drawn this picture. You see this, there are 3 beakers, and there are 3 colors. This means 3 different lights, 3 different wavelengths. Okay. The summary of the result is that if you put different lights, okay, in this beaker, you have different amount of oxygen. Okay. But if you do the same thing in water, it doesn't happen. So I asked the editor, do you know any system that you can control the amount of oxygen inside a beaker by using an external torch, a laser light? And then, of course, the editor accepted it, and it has gone for review. It is still in review. So it is fantastic, right? So if you have a beaker and if you have light like this, you see the oxygen level in the light is less, but outside the light is more. And if you can make something like this in a beautiful picture inside a beaker, and you have a landscape of oxygen, somewhere more, somewhere less, somewhere too less. So you can control this from outside. So basically, most of the slides are conclusions only, because I did not explain the science behind it. So a novel, what I showed is that we connected it to plastic and nanomaterials and catalysis and energy harvesting and chemical reactions, right? So I showed you how carbon dots can be made from waste plastic, then how it can do oxygen harvesting and oxygen enrichment, oxygen harvesting from air, oxygen enrichment on the catalyst, okay, improved O2 diffusion, then use of free air for oxidation reactions, and then spontaneous elimination or autophagy, and hypoxia, the last thing. Yeah, so with this, I think carbon dot can become, if we can find further applications, this can become as important as something like graphene or carbon nanotube or fullerene someday. So with that, I thank you all, and thank you. So I'll be happy to take any questions if I have.
Thank you, Ujjal. So starting from very basic to very high level of chemistry and real life research experience, মই ভাবো আমাৰ ছাত্ৰ-ছাত্ৰীসকলে যথেষ্ট উপকৃত হৈছে। তেওঁলোকে মানে একেবাৰে সাধাৰণ তেওঁলোকৰ বেছিক আণ্ডাৰষ্টেণ্ডিঙৰ পৰা গৈ কেনেকে আমাৰ গৱেষণাবিলাক চলি থাকে, কিমান ষ্ট্ৰাগল থাকে, কেনেকে নতুন বস্তু এটা উদ্ভাৱন হয়, তাৰ কিমান পৰীক্ষা নিৰীক্ষাৰ পিছত বস্তুটো মানে এষ্টাব্লিছ হয়, মানুহে গ্ৰহণ কৰে, গোটেই এটা অভাৰঅল আইডিয়া এটা পাইছে বুলি মই আশা কৰিছোঁ ছাত্ৰ-ছাত্ৰীসকলে। মানে ফ্ৰম বেছিকৰ পৰা আৰম্ভ কৰি তেওঁলোকে কিতাপত যিবিলাক পঢ়ি কথাবিলাক যে কিমান এটা দীঘল প্ৰচেছৰ মাজেদি কিমান পৰীক্ষা নিৰীক্ষাৰ মাজেদি গৈ এনেকুৱা এটা অৱস্থা পাইগৈ, তাৰ এটা ফাৰ্ষ্ট হেণ্ড এক্সপিৰিয়েঞ্চ পালে বুলি মই আশা কৰিছোঁ। ছাত্ৰ-ছাত্ৰীসকল, তোমালোকৰ যদি কিবা কুৱেশ্যন আছে, তোমালোকে ডাইৰেক্ট মাইক্ৰফোনটো অন কৰিও সুধিব পাৰা, আৰু ইয়াত জুমতো লিখি দিব পাৰা। আমাৰ অলৰেডি কেইটামান কুৱেশ্যন আহিছে ইয়াতে, মই অলপ পঢ়ি দিওঁ তাৰে হেৰি কেইটামান। প্ৰথমটো আহিছে সাজাদুৰ ৰহমান হাজৰিকা, 5th semester, শিৱসাগৰ কলেজ, জয়সাগৰ। Are there any specific health or other risks from nanoproducts?
Okay.
Mm,
This is very important questions, and the answer is yes and no. So, see, nanomaterials field is about say 20-25 years old, and
Ujjal, probably you can remove this one slide so that your face will be visible in the discussion time.
So this is a very important question. I think this is the most burning question, one of the most burning questions in this field. Toxicology, the toxicity of nanomaterials, because they are very small, much smaller than size of the cells. Okay, cells of animals and human and plants. So, and it can go with water. Okay, there is very little gravitation effect of gravitation on nanoparticles. So it can float, it can go with water, and the cell walls, it can penetrate cell walls. Many nanomaterials can penetrate cell walls. And then, for example, deodorant nowadays, many deodorant, তোমালোকে যিটো লোৱা হয় তোমাৰ হাতৰ তলত তেনেকৈ ডিঅডৰেণ্ট লোৱা হয়, তাত সিলভাৰ নেনোপাৰ্টিকল থাকে। সো সিলভাৰ এনিৱে, সিলভাৰ নেনোপাৰ্টিকলে যিবিলাক বেক্টেৰিয়েল গ্ৰোথ হয়, আমাৰ ভিতৰত যিটো বেক্টেৰিয়েল গ্ৰোথ হয়, তাৰ সেল ওয়ালটো ডিস্টার্ব কৰিব পাৰে। সো এইটো তাৰমানে বেক্টেৰিয়াৰ কাৰণে টক্সিক, কিন্তু আমাৰ বডিবিলাকতো তেনেকুৱা ধৰণৰ সেল থাকে। গতিকে yes, many of them are toxic, but many of them are not. For example, carbon dot. So বহুত বেছি ইনফরমেশন নাই এইবিলাকৰ ওপৰত, কাৰণ এইবিলাক নতুন বস্তুটো। কেতিয়া কিছুমান বস্তু বেয়া হয় হয়তো কেইদিনমানতে গম পাবা, কিছুমান বস্তু বেয়া হয় it takes several years to know. So এতিয়ালৈকে যিমানখিনি জনা গৈছে যে বহুত বেছি মানে বেয়া নহয় বস্তুটো। কাৰ্বন ডট ইমান বেয়া নহয়, কাৰণ এইটো কাৰ্বন হয়, আমাৰ বডিটো কাৰ্বন আছে, মানে এইটো এবজৰ্ব কৰি লয়। কাৰ্বন ডটো তেনেকৈ কাৰ্বন নেনোটিউব তেনেকৈ এইটো এক্সক্ৰিট কৰিব পাৰে কিছুমান। গতিকে বহুত ইম্পৰ্টেণ্ট কুৱেশ্যন, বাট আনচাৰটো মানে কমপ্লিটলি জনা নহয় এতিয়াও। দুই ধৰণৰ কাৰ্বন নেনোটিউব আছে, নেনোমেটেৰিয়েল আছে।
আৰু এটা কুৱেশ্যন আছে আপোনাৰ সৌভিক ফুকন তুমি সুধিবা নেকি কুৱেশ্যনটো নিজে, নে মই পঢ়ি দিওঁ?
স্যার আপনি পঢ়ি দিও মানে।
ঠিক আছে। কুৱেশ্যনটো হৈছে, is there any other synthesis method or reaction from which we can synthesize carbon quantum dot apart from dehydrating graphene by H2SO4?
এইটো ইণ্টাৰেষ্টিং কুৱেশ্যন। একচুৱেলি এটা নহয়, বহুত মেথড আছে। তুমি যদি মানে তুমি অলপমান ভাতো লৈ পেলাই, যদি ভাত অলপমান লৈ পেলাই তুমি তাত ধৰা H2SO4 বা এনেকুৱা তুমি প্ৰেছাৰ কুকাৰত বহুত দেৰি মাৰি থাকা, সেইটোৰ পৰাও কাৰ্বন ডট হয়। অলপমান ভাত বা তোমাৰ সলভেণ্টটো চেঞ্জ কৰিব লাগিব, ৱাটাৰত নহয়। যিকোনো বস্তু কাৰ্বন থকা বস্তু, কাৰ্বনটো বহুত ষ্ট্ৰং নহ'লেই হ'ল। গ্লুক'জ, চুগাৰ, বাৰ্লি, যিকোনো বস্তুৱে তুমি যদি অলপমান হিট কৰা, তোমাৰ ধৰা এলকহলত বা ক'ৰবাত, আৰু কিছুমান ৰিয়েক্টেণ্ট যদি দি দিয়া, খুব সহজেই বনি যায়, একদম সহজ। কিন্তু প্ৰব্লেম আছে, অন্য কিছুমান প্ৰব্লেম আছে। ধৰা অকল কাৰ্বন ডটেই নহয়, আৰু তাৰ লগত বহুত কিবা কিবি হয়। তাৰপিছত সিহঁতৰ ছেপাৰেট কৰাটো বহুত ডাঙৰ প্ৰব্লেম এটা। আমি যিটো ডিছকাছ কৰিলোঁ, সেইটো চিন্থেচিছটো তোমাৰ H2SO4 দিয়া এইটো ইমান ভাল নহয় যেন লাগে, কিন্তু তোমাৰ ছেপাৰেট কৰাটো সহজ। কিছুমান ছেপাৰেট কৰোঁতে তোমাৰ 3-4 দিন লাগি যায়, এইটো ধৰা মই 15 মিনিটত ছেপাৰেট কৰিব পাৰোঁ। এই তেনেকুৱা এডভান্টেজ আছে, কিন্তু এনে বহুত মেথড আছে কাৰ্বন নেনো ডট বনোৱা।
আশিষ বৰাই আৰু এটা ইণ্টাৰেষ্টিং কুৱেশ্যন সুধিছে। কৈছে, থেংক ইউ ছাৰ ফৰ দিছ গ্ৰেট ছেশ্যন। Sir, as you told, carbon is cheap and it is easily available. Why graphene is so much costly?
মই নাজানো তুমি ক'ৰ পৰা কিনিছা। কেতিয়াবা এই দালাল চালা আহে মাজত, সিহঁতিও মানে অলপ পইচাটো বঢ়াই দিয়ে। তাৰপিছত তোমাৰ আচলতে গ্ৰাফিন টু চিপ হয় যিকোনো তোমাৰ মই যে কৈছো তোমাক প্ৰথম ডিস্কভাৰ কৰিছে পেন্সিলৰ পৰাই পেন্সিলৰ নিচিনা বস্তু এটা এইচঅপিজি বুলি কয় পেন্সিল নহয় একজেক্টলি যেতিয়া আমি কেমিকেল এক্সপেৰিমেন্ট কৰোঁতে বস্তুটো ডিপেন্ড কৰে পিউৰিটিৰ ওপৰত যদি বস্তুটো এক্সট্ৰিমলি হাইলি পিউৰ লাগে তোমাৰ 99.9% এনেকুৱা ধৰণৰ পিউৰ লাগে গ্ৰাফিন বুলি ক'লে তুমি এটা মনত এটা পিকচাৰ আহে যেনেকৈ হেক্সাগনাল ৰিংবিলাক সব কানেক্ট হৈ আছে কিন্তু সঁচাকৈ যেতিয়া ইহঁতক বনোৱা যায় সববিলাক ধৰা হেক্সাগনাল নহয় তাত তোমাৰ 100টাত এটা বা দুটা এনেকুৱা থাকিব যাত পেন্টাগন থাকিব বাট ক'ৰবাত যিটো কাৰ্বন হয় ক'ৰবাত OH এটা লাগি আছে ক'ৰবাত COH এটা লাগি আছে বনাওঁতে এনেকুৱা হৈ যায় এতিয়া তুমি যেতিয়া এটা বস্তু লেবৰেটৰী কিনা হয় লেবৰেটৰীৰ কাৰণে কিনা হয় এইটো পাৰফেক্ট বস্তু এটা কিনিব লাগে এই এনেকুৱা ডিফেক্টবিলাক যিমান থাকে কম হ'ব লাগে বা প্ৰত্যেকবাৰ কিনোতে একেধৰণৰ বস্তু কিনিব লাগিব যে তুমি আজি এটা এক্সপেৰিমেন্ট কৰিছা এবছৰৰ পিছত এটা এক্সপেৰিমেন্ট কৰিছা ৰিজাল্টবিলাক একে আহিব লাগিব গতিকে সেই কিছুমান প্ৰসেস অপটিমাইজেশ্যন কৰা হয় প্ৰসেস অপটিমাইজেশ্যন কৰোঁতে বহুত মানুহ ইনভলভ থাকে পেটেন্ট থাকে সেইকাৰণে দামটো বহুত এক্সপেন্সিভ হৈ যায় কিন্তু তুমি যদি ঘৰত বনোৱা তুমি যদি জানা কেনেকৈ বনায় তোমাৰ ধৰা এচিড বহুত সস্তাতে পোৱা যায় কাৰ্বন বহুত সস্তাতে পোৱা যায় গতিকে কাৰ্বন কি তুমি সেই যে এতিয়া তোমাৰ মেজিত যিটো জুই জ্বলোৱাৰ পিছত পিছদিনা যিটো থাকি যায় সেইটোৰ পৰাও গ্ৰাফিন বনাব পাৰি এইটো একদম সস্তাতে হৈ যাব
নীলকমল আৰু কিবা কোৱেশ্যন আছে নেকি
ৰিফাত দা ফেচবুক আৰু ইউটিউবৰ পৰা এবাৰ চাই দিবচোন
এটা প্ৰশ্ন দেখিছো যে মানে এইটো কোনোবা এজনে জানিব বিচাৰিছে যে ছাৰ আপোনাৰ মানে এইটো ৰিচাৰ্চ ফিল্ডৰ বিষয়ে ক'ব নেকি আপোনাৰ ফিল্ড অফ ইণ্টাৰেষ্ট
আচ্ছা মই যিখিনি কাম কলো আজি সেইখিনি মোৰ লেবতে হোৱা কাম সেইখিনি আমাৰ মোৰ ইণ্টাৰেষ্টবিলাক তেনেকুৱাই আছে আমাৰ লেবত দুই ধৰণৰ কাম হয় এটা ফটোকেমিষ্ট্ৰিত হয় এটা ইলেক্ট্ৰকেমিষ্ট্ৰিত হয় আমি বেচিকেলি এনাৰ্জি হাৰ্ভেষ্টিঙত কাম কৰোঁ আৰু এনাৰ্জি হাৰ্ভেষ্টিং হ'ল যিটো সঁচাকেই এনাৰ্জি বুলি কয় তোমাৰ গাড়ী চলোৱা এনাৰ্জি তেনেকুৱা ধৰণৰ বা ইলেক্ট্ৰিচিটি বাট কিছুমান উই অলছ' ডু চিম্পল ফটোকেটালাইটিক ৰিয়েকশ্যনছ যিটোত মানে ধৰা তোমাৰ ৰিয়েকশ্যনটো ধৰা তুমি 80 ডিগ্ৰীত 90 ডিগ্ৰীত কৰে তেনেকুৱা ৰিয়েকশ্যনবিলাকো আমি জাষ্ট ছানলাইট লৈ পেলাই ৰুম টেম্পাৰেচাৰত কৰিব পাৰি নেকি ত' সেইটো ইনডাইৰেক্টলি ডেট ইজ অলছ' এনাৰ্জি হাৰ্ভেষ্টিং ইউজিং ছানলাইট So in general, three parts. We have a group, electrochemistry group, we have a photochemistry group, and we have a simple conventional catalysis group, photocatalysis, organic chemistry.
আৰু উজ্জ্বল দা আপুনি আমাৰ ল'ৰা ছোৱালীখিনিৰ কাৰণে ক'ব নেকি কেনেকৈ ইহঁতে আগবাঢ়ি যাব পাৰিব বা যদি চাইন্স কৰিব বিচাৰে কি ধৰণৰ এডভাইচ দিব বিচাৰিব আপুনি সিহঁতক যিসকলে ধৰক ভৱিষ্যতে সায়েন্সৰ ফিল্ডত আহিম বুলি ভাবিছে
তাৰ আগতে আৰু এটা প্ৰশ্ন আহিছে এইটো উত্তৰ দি ল'ব পাৰে উজ্জ্বল দাই উজ্জ্বল দাই সুধিছে যে এই বছৰ নোবেল প্ৰাইজ পাইছে যে ফটোকেটালিসিস নট ফটোকেটালিসিস অৰ্গেনোকেটালিসিস তাৰ বিষয়ে অকমান ছাত্ৰ ছাত্ৰীক থুলমূলকে ক'ব পাৰিব নেকি সিম্পল ভাষাত
মই পটককে ক'ব নোৱাৰিম দেই মই ৰিয়েকশ্যনখিনি আৰু বেলেগ কুৱেশ্যন আছে নেকি মই এইটো কথা ভাবি আছো
কল্যাণ দাই সোধাটো কৈ লওক নহলে যদি এইটো
এক মিনিট লৈছো মই সেইটো মই জানো কাৰণ বস্তুটো অৰ্গেনিক কেটালাইসিছত অৰ্গেনিক কেমিষ্ট্ৰি হয়তো বেলেগ কোনোবাই জানিব পাৰে ইয়াত থকা মই স্পেচিফিক ৰিয়েকশ্যনটো মানে why it is so important I don't know how it is different from others
এবাৰ নীলকমলে এটা প্ৰবন্ধ লিখিছে উজ্জ্বল নীলকমল আছে নেকি নীলকমলে সেই বিষয়ে এটা প্ৰবন্ধ এটা লিখিছিলে
নীলকমলে ক'ব পাৰে এইটোতো
নাই তেনেকুৱা মানে বিশেষ ডিফাৰেন্স আছে সো অৰ্গেনিক ইউজুৱেলি ক্যাটালিসিস বা সংঘটক যেটো বিদ্যা বা অনুঘটন প্ৰক্ৰিয়াত যোনটো উজ্জ্বল দাই আজি কৈ আছে ফটোক্যাটালিসিস ইউজ কৰি আইদাৰ মেটেলস ইউজ হয় ধাতু হাই লাইক প্যালেডিয়াম প্লাটিনাম হে আৰু বা অৰ্গেনিক আমাৰ বায়োলজিত যোনবিলাক হয় এনজাইমছ বুলি বায়োক্যাটালিসিস বুলি কয় কিন্তু দুইটাৰে বিভিন্ন ধৰণৰ লিমিটেশনস আছে তো এই বেঞ্জামিন লিস্ট যোনজনে এবাৰ নোবেল প্ৰাইজ পাইছিলে 2000 চনত তেওঁ প্ৰলিন নামৰ এবিধ যোনটো এমিনো এসিডছ হয় সাইক্লিক এমিনো এসিড আৰু প্ৰলিন ইউজ কৰি which is non polluting and amino acid use কৰি তেওঁ দেখুৱাইছিল যে ৰিঅ্যাকশন বিলাক ক্যাটালাইজ কৰিব পাৰি so those are organic molecules not any metallic impurities or polluting metals plus these are not also sensitive to oxygen and water so many metals are sensitive to oxygen and water so heavy metals or বিলাক limitations আছে তাৰপিছত যোনজন আদাৰ সাইন্টিস্ট আছিল তেওঁ ডেভিড মেকমিলান বুলি তেওঁ ফটোক্যাটালিসিসৰ ওপৰতো কাম কৰে ইউনিভাৰ্সিটি অফ প্ৰিন্সটনৰ সো তেওঁ তেনেকুৱা সাৰ্কুলাৰ এমিনো এসিড ইমিডাজলিডিনন বুলি কয় আৰু মলিকুলটো তেওঁ দেখাইছিল যে 2000 চনতে প্ৰায় ইন্ডিপেন্ডেন্টলি the reaction catalyze কৰিব পাৰি without using metals using this small organic molecules circular shaped which also have the same efficiency কিন্তু লিমিটেশনস বিলাক নাই যেনেকৈ ধৰক পলিউশন বা ইটস লাইক মোর অফ এ গ্ৰীন কেমিষ্ট্ৰি আৰু সেই মলিকুল বিলাক are like part of the body let's say proline so hey দুটা বিষয় আৰু so it's another type of catalysis using organic molecules avoiding metals and also the big protein molecules like enzymes so হেইটোৱে আৰু বিশেষ so এই বছৰ কি বিজ্ঞান জ্যোতিত কথাটো ওলাইছিলে এটো এই বছৰ নোবেল প্ৰাইজৰ বিষয়ে বাট কোনবাই সুধিছিলে সেইকাৰণে মই মানে ফটো আপোনাৰ ক্যাটালিসিসৰ ওপৰত যেহেতু আছিলে সেইকাৰণে হয়তো সেই প্ৰশ্নটো উদ্ভাৱন হৈছিলে কাৰোবাৰ মনত
আচ্ছা
থ্যাংক ইউ
নীলকমল ধুনীয়াকৈ কৈ দিয়াৰ কাৰণে
কল্যাণদাৰ প্ৰশ্নটোৰ কাৰণ সেই প্ৰশ্নটো আমাৰ প্লেটফৰ্মত সদায় আহে কেনেকে হায়াৰ ষ্টাডিজ কৰিব পাৰি আৰু আপোনাৰ
অসমৰ ৰাষ্ট্ৰবিলাকৰ মানে অকমান আৰাউণ্ড এনকাৰেজমেন্ট এটা বা গাইডলাইনছ এটা যেটা আমাৰ মানে প্লেটফৰ্মটোৰ এটা অন্যতম হাৰি আৰু মটো the last বিলাক অকমান মানে দুআষাৰ এনকাৰেজ কৰিলে
মই কি কম মইতো তাৰ পৰাই অহা আৰু ইয়াত সবেইতো ক'বাত নহয় ক'বাত ষ্টাৰ্ট কৰে লং জাৰ্নি ষ্টাৰ্ট হৈছে বেবি ষ্টেপছ ৰৈ নগলেই হ'ল এইটো দিগদাৰী বুলিবলৈ এইটো মই একোৱেই নেদেখোঁ প্ৰথমতে বিএসসি কৰিব লাগিব বিএসসি যেটো সময় যেটো কৰি থকা আছে তো ভালকে কৰিলে হ'ল ৰিসাৰ্চত দুই ধৰণৰ পঢ়া থাকেতো এটা নম্বৰ পোৱাটো বহুত দৰকাৰী আৰু তাৰপিছত হলেও বস্তুখিনি বুজিও পাব লাগে বেছি সময়ত বেছি বস্তুখিনি ভালকে কৰা আৰু যদি 5-10% টাইম পোৱা তুমি অলপ বাহিৰৰ বস্তু অলপমান জানি থাকিব লাগে ৰিসাৰ্চত কি হৈ আছে বা প্ৰবলেম বিলাক কি ৰিসাৰ্চটো তেতিয়াই ভাল হয় যেতিয়া প্ৰবলেমটো যেতিয়া ভাল প্ৰবলেম চুজ কৰা যায় তেতিয়াহলে ৰিসাৰ্চটো ভাল হয় আৰু কেতিয়াবা এক্সিডেন্টালিও বহুত ৰিজাল্ট পোৱা যায় তেনেকেও ৰিসাৰ্চটো ভাল হয় কিন্তু বেছি কৰি থকা সময়ত বেছি মানে মন দিয়া এমএসসি কৰি থকা সময়ত এমএসসি বস্তুখিনি মন দিয়া অলপমান নিজৰ অলপ খবৰ খাতি ৰখা আৰু বাকি কি হৈ আছে এইটো সবতকৈ ইম্পৰ্টেন্ট কথা আৰু কিন্তু মই যিমানখিনি মানুহ লগ পাইছো কিছুমানৰ ৰিসাৰ্চ কৰা মন থাকেই গতিকে মন নাথাকিলে কৰিব নালাগে মন থাকিলে কৰিব লাগে সব প্ৰফেশনেই ভাল সব প্ৰফেশনেতে চ্যালেঞ্জ আছে আৰু আসলতে সব প্ৰফেশনতে ৰিসাৰ্চ আছে তুমি যদি দোকান এখনো দিয়া তুমি হয়তো ক'বাত ভাবিব লাগিব ইয়াত পাচলিৰ দোকান দিও নে হোটেল দিও নে কোনটো দিলে কেনেকৈ গোটেইখিনি বস্তু ভবা যায় অলপ ৰিসাৰ্চ কৰিবলগীয়া হয় কি দোকান আছে আহে পাহে সো ৰিসাৰ্চ বিলাক তেনেকুৱাই বস্তু দূৰৰ পৰা অকমান ডাঙৰ যেন লাগিলেও কিন্তু ভিতৰলৈ সোমাই গৈ থাকিলে বস্তুবিলাক ভাঙি পেলালে সৰু ষ্টেপত তেনেকুৱা সৰু ডিসিশনে ল'বলগীয়া হয় So কিছুমান ডিফিকাল্টি থাকে এটা ডিফিকাল্টি হল যে দীঘলীয়া প্ৰচেছটো দীঘলীয়া PhD MSc PhD postdoc তাৰপিছত ইণ্ডিয়াত মানে এখন ভাল জায়গাত ৰিসাৰ্চ কৰিবলৈ পোৱা যায় পাৰ্মানেন্ট ফেকাল্টি হৈ পেলাই ইণ্ডিয়াত যি ধৰণৰ প্ৰবলেম আছে প্ৰবলেমটো হল যে আমি ইন্ডাষ্ট্ৰি ড্ৰিভেন কান্ট্ৰি নহয় গতিকে আমাৰ প্ৰবলেম বিলাক একাডেমিক প্ৰবলেম হয় সাধাৰণতে যিবিলাক দেশত ইন্ডাষ্ট্ৰি ড্ৰিভেন হয় সিহঁতে ইন্ডাষ্ট্ৰিৰ প্ৰবলেম বিলাক পাই থাকে ইটস এ সিম্পল জব ওকে উই নো সাম টেকনিক্স স্ট্যান্ডার্ড কান্ট্রি বিলাকত মানে হেৰি এডভান্স কান্ট্রি বিলাকত যে যিবিলাক ইন্ডাষ্ট্ৰিৰ প্ৰবলেম পায় প্ৰবলেমটো সুধিবলৈ আহে যেনেকৈ ডক্টৰৰ ওচৰত যায় তেনেকৈ সাইন্টিষ্টৰ ওচৰত আহি এই প্ৰবলেমটো কেনেকৈ সলভ কৰিব পাৰি আৰু যেহেতু কোনো এজন মানুহ এইটো ওপৰত স্পেশালিষ্ট হয় গতিকে তেওঁ সলিউশনটো দিয়ে আৰু সেইবিলাক কৰি থাকোতে কিছুমান আনইউজুৱেল বস্তু পাই যায় তাৰ সেইবিলাক বস্তু তেতিয়া বহুত ভাল হৈ যায় কিন্তু it is not something great it's a good tradition very good career but all careers are good and all careers you have to do research you have to if you want to rise so you just if you like research and if you do not get frustrated you should not get frustrated and just hold on to what you like and just এটা কৰি BSc কৰা MSc কৰা তাৰপিছত যদি বেসিক্স খিনি ভাল হয় কোবাত তুমি PhD পাবা তুমি যেটো সাবজেক্ট ভাল পোৱা হেতু সাবজেক্টতে PhD কৰিব লাগে অনেক কি কয় হেতু ইম্পৰ্টেন্ট কথা নহয় আৰু তেনেকৈ গৈ থাকিলে বস্তু ভিতৰত সোমাই থাকিলে নেটেকে হৈ যায়গে very simple answer I think
thank you Ujjal but very effective so মানে আমি কথা কোতে হে আমাৰ পল্লৱী গোস্বামী বাইদেউৰ যেতিয়া কথাটো কৈছিলে তেতিয়া লিংকটো কাটি গৈছিল আমি তেখেতৰ বক্তব্য যদি ৰাখিব বিচাৰে আমি অনুৰোধ জনাইছো যাতে তেখেতৰ কথা কয়
হয় থ্যাংক ইউ আসলতে তেতিয়া হঠাতে লিংকটো নাইকিয়া হৈ গল মই নিজেও গম পোৱা নাছিলো খুবেই ভাল লাগিল আৰু এক প্ৰকাৰ নিজৰে মানে ছাত্ৰ জীৱনলৈ ঘূৰি যোৱাৰ নিচিনাই লাগিল কথাখিনি শুনি আৰু আমাৰ ষ্টুডেন্ট সকলো নিশ্চিতভাৱে খুবেই উপকৃত হৈছে মই পুনৰাই কল্যাণ ৰাইডঙিয়াকে প্ৰমুখ কৰি সকলোকে আন্তৰিক কৃতজ্ঞতা জনাইছো আমাক এই অনুষ্ঠানটোত অংশগ্ৰহণ কৰিবলৈ সুবিধা দিয়াৰ বাবে যদিও মই নিজে ফলো কৰো বা বাকি অনুষ্ঠানবিলাকতো আমি সাধাৰণতে থাকুৱেই তথাপি আজি গৌতম ডাঙৰীয়াৰ পৰা এই কথাখিনি ইমান প্ৰাঞ্জলভাৱে আৰু ইমান সৰলভাৱে জানিব পাৰিলো মই সকলোকে আন্তৰিক শুভেচ্ছা দিছো আৰু ভৱিষ্যতেও ইয়াৰ লগত জড়িত হৈ থাকিবলৈ পালে ভাল পাম
ধন্যবাদ বাইদেউ ৰিফাত দা আপোনাৰ
হৰে উজ্জ্বল
স্যাৰ
মই চহৰীয়া কৈছো
স্যাৰ গম পাইছো
তা মই এটা প্ৰশ্ন এটা মোৰ মনলৈ আহিছে CQD is a good conductor no
good conductor
so
it should be
it is a good conductor and carbon has the property as similar to the silicon or germanium so is there a chance that CQD will replace the conventional semiconductor devices in future
silicon or হেৰিটো silicon যেটো মানে হেৰিয়াত ইউজ ডিভাইসত ইউজ কৰা হয় ডিভাইসত ইউজ কৰা নরমালি ব্ল্যাক থিন ফিল্ম ফিচার সাইজ বিলাক হয় আপোনাৰ যদি এটা ফিচার সাইজ হয়তো ন্যানোমিটার হ'ব বাট বেসিক্যালি এসেনশিয়ালি দে আর থিন ফিল্মস at least the other dimensions are about say 100 nanometers but maybe thickness is 4-5 nanometer so that you can make the connections and make a device carbon dot is too small to make a connection so I do not know difficult to predict but I think it is as of now it is difficult
no okay and CQD doping of কথা আছে নেকি বাৰু is there some kind of a doping in CQD
actually CQD if we define my personal definition is that a few carbon atoms which is like graphite but with a lot of junk. Even in fact, nobody knows where the color comes from. The color normally the color comes because if you have, for example, benzene doesn't have color because it absorbs in the UV region. If you put two benzene rings together, naphthalene, then if you keep increasing the conjugation, or if you take conversely, if you take a very small graphene piece, then it can have colors because of conjugation. Now, if there are many these 6-member rings, then it also absorbs all the light, so it is carbon is black. So the molecules here which is responsible for color are actually not exactly graphene. So these are some functional molecules which get generated during the synthesis process, and there's a lot of confusion about what is the origin of color. So in my research, I never addressed this because I found that I cannot explain this. So now so what I mean to say is that it is a mess. So in this, it is possible to replace some of the carbons with nitrogen and boron.
Okay.
Yes. But it is already carbon dot is in some sense, it is like doped because it has some other molecules attached to it by default.
Okay. See. Thank you.
Maybe Rifadda can share the screen for the next session.
My screen to share কৰি দিছো ৰবা।
By that time হেতু হয় এটা আৰু প্ৰশ্ন আহিছে উজ্জ্বল দালে। উজ্জ্বল দা এজন ষ্টুডেন্টে জানিব বিচাৰিছে যে আইজাৰত যোনটো BSMS প্ৰগ্ৰাম হয় মানে IIT আপুনি অলপ আৰম্ভণিতে কৈছে কথাটো যে এডভান্সড বা KVPY বা আইজাৰ টেষ্টৰ পাৰ কৰি যাব পাৰি, হেতু আমাৰ গ্ৰেজুৱেচন বা আমাৰ নৰ্মেল আসামৰ কলেজ বা দিল্লী ইউনিভাৰ্চিটি কলেজৰ BSc CSc কে কিমান বেলেগ হয় আৰু কি এক্সট্ৰা কম্পোনেন্ট থাকে আৰু হেতু পঢ়ি ষ্টুডেন্ট খিনি ক'ত যাব পাৰে?
এটো আইসাৰ এডমিশন টেষ্টটো বা এনেটো IIT পৰা আহে আমাৰ IIT পৰা আহে অলমোস্ট 50% IIT পৰা আহে IIT এডভান্স আৰু বাকিখিনি আহে তো আমাৰ নিজৰ যিটো টেষ্ট হয় মই তাৰ লিংকটো ইয়াত পঠাই দিছো সো ইয়াত চালেই গম পাব এই হেৰিয়াৰ নিচিনাই এটা টেষ্ট হয় IIT জেইৰ নিচিনাই এটা টেষ্ট হয় যেটো আইসাৰ বিলাকে একেলগে গোটেইখিনি আইসাৰ একেলগে কন্ডাক্ট কৰে আৰু তাত সিলেকশন হলেও তাত জয়েন কৰিব পাৰে
আৰু প্ৰগ্ৰাম কাৰিকুলামটো কিমান বেলেগ হয় ৰিসাৰ্চ কম্পোনেন্ট বহুত থাকে নেকি
আচ্ছা এবাৰ জয়েন কৰাৰ পিছত ইয়াত ফ্লেক্সিবল বহুত ফ্লেক্সিবল প্ৰথম কথা হল জয়েন কৰিয়ে কি হয় ধৰা কোনবাই জয়েন কৰিলে আইসাৰ মহালি কাৰণ গোটেইটো এটাই টেষ্ট হয় গোটেইবিলাক আইসাৰৰ কাৰণে তাৰপিছত বলে কোনবাই নহয় মই আইসাৰ কলকাতা যাব খুজো কাৰণ অসমৰ পৰা ওচৰত প্ৰথম কথা ফ্লেক্সিবিলিটিটো প্ৰথম এসপ্তাহৰ ভিতৰতে পায় সেই ফ্লেক্সিবিলিটি থাকি গোটেই আইসাৰ ষ্টুডেন্টখিনিক কোৱা হয় নতুন ষ্টুডেন্টখিনিক যে তহঁতি যদি ট্ৰান্সফাৰ অপচন দিব পাৰো আৰু কি হয় কোনবাই যদি কলকাতাৰ পৰা বলে পুনেলৈ গ'ল পুনেৰ পৰা মহালিলৈ আহিলে মহালিৰ পৰা কলকাতালৈ গ'ল এনেকে বহুতখিনি এডজাষ্ট হৈ যায় প্ৰথম হেতু এডজাষ্টমেন্ট তাৰ পিছত নিজৰ হেৰিটো পোৱাৰ পিছত নিজৰ ভাল লগা ইনষ্টিটিউটখন পোৱাৰ পিছত তাৰ প্ৰথম 2 বছৰ সব কোৰ্স পঢ়িব লাগে আৰু তাৰ পিছত প্ৰত্যেকটো ইন্টাৰ আৰু প্ৰত্যেকটো সামাৰত কোনবা এটা ল্যাব জয়েন কৰি পেলাই ইন্টাৰ প্ৰজেক্ট আৰু সামাৰ প্ৰজেক্ট কৰিব লাগে তো সেইখিনি কৰি থাকোতেই আসলতে ষ্টুডেন্ট বিলাকে নিজে ডিসকভাৰ কৰে যে মানে ফিজিক্সত ভাল নে কেমিষ্ট্ৰিত ভাল নে বায়োলজিত ভাল নে ম্যাথছত ভাল বা হিউম্যানিটিজ so they can decide and সেইখিনি ডিসিশন লোৱাৰ পিছত এতিয়ালৈকে কোনো আইসাৰ এনেকুৱা ৰুল নাই যে 30টা ফিজিক্সত যাব 30টা কেমিষ্ট্ৰিত যাব so যিটো বিচাৰে সি হেতুত যাবই পাৰে কোনবা ফিজিক্সত বিচাৰিলে ফিজিক্সত সাধাৰণতে যাব পাৰে যদি এটলিষ্ট এক্সাম বিলাক একদম বেয়া নহয় গতিকে ধৰা যেটো CPI টো যদি 6 পায় 10ৰ ভিতৰত 6 পায় তেতিয়াহলে যিকোনো সাবজেক্ট ল'ব পাৰে বাট এনেকে এটো নেক্সট ফ্লেক্সিবিলিটি তাৰ পিছত থাৰ্ড ইয়াৰ পৰা এটো মেজৰ হয় থাৰ্ড ইয়াৰ ফ'ৰ্থ ইয়াৰ মেজৰখিনি পঢ়িলে তাৰপিছত পুনতে আকৌ সেই যিটো মানে প্ৰজেক্টটো চলিয়ে থাকে প্ৰত্যেক সামাৰতে উইণ্টাৰতে আজিকালি আৰু ইম্প্ৰুভ হৈছে যে সেই প্ৰজেক্টবিলাক তাৰমানে বেলেগ আইচৰত গৈ বা আইআইটিত গৈ ইনফেক্ট ফৰেনত গৈও কৰিব পাৰি তাৰপিছত কি হয় যে ফিফথ ইয়াৰটো মানে আমাৰ যিটো নাম আছে ইণ্ডিয়ান ইনষ্টিটিউট অফ সায়েন্স এডুকেশ্যন এণ্ড ৰিচাৰ্চ ফিফথ ইয়াৰটো কমপ্লিট এটা ৰিচাৰ্চ প্ৰজেক্ট কৰিব লাগে যেনেকৈ PhD বিলাকে কৰে from beginning to the end এটা কনক্লুজন অহালৈকে যাতে মানে ষ্টুডেণ্টজনৰ এটা আইডিয়া হৈ যায় যে ৰিচাৰ্চটো কেনেকৈ কৰে প্ৰব্লেমটো লাগে সৰুৱে হওক কিন্তু গোটেইখিনি বস্তু সলভ কৰিবলৈ এখন থিচিছ লিখিব লাগে so the idea is that the student is ready to take the real research problems and they know the difficulties in research life and how to adapt so tenukai system too but it is different from কিছুমান ইউনিভাৰ্সিটিত য'ত মানে এক্সপোজাৰটো অলপমান বেছি হয়
সো মানে এটো এটা পাৰ্সোনাল প্ৰশ্ন যে আমাৰ আপুনি দিল্লী ইউনিভাৰ্সিটিত পঢ়িছে বা আমি বিলাকও পঢ়িছো বা ধৰক অসমৰ কলেজ বিলাকতো এই ৰিসাৰ্চ কালচাৰটো একেবাৰেই নাই মোস্ট লাইকলি প্ৰ্যাকটিক্যাল গিটা হয় আৰু টানি থুনি আৰু আপোনাৰ ৰইলক আৰু কোৰ্সটো কমপ্লিট হয় আৰু সেই আন্ডাৰগ্ৰেজুৱেট এডুকেশনত সেই ৰিসাৰ্চটো সম্পূৰ্ণৰূপে নাপায় গতিকে ধৰক আইজাৰ বিলাকে তেনেকুৱা অলপ কিবা কৰিব পাৰে নেকি যে বাহিৰৰ ষ্টুডেন্টকো যাতে অলপ চান্স দিব পাৰে তেনেকুৱা অপচন আছে না ইন্টাৰ্নশিপ বা এনেকুৱা যাতে কোনোবাই গৈ আইজাৰ প্ৰজেক্ট কৰিব পাৰে বিএসসি বেলেগত কৰি থকা
ঠিক আছে তুমি দুটা কথা ক'লা এটা হ'ল এই যে মানে ৰিসাৰ্চ কালচাৰটো যে ভাল এটোৰ পৰা এতিয়া আমি কেনেকৈ গম পাইছো যে ইয়াৰ ষ্টুডেন্ট বিলাকে বিএসএম ষ্টুডেন্ট বিলাক সাধাৰণতে বাহিৰত পিএইচডি কৰিব যায় আৰু হিহঁতি যিমান বিলাক এপ্লিকেশন কৰে অলমোস্ট সববিলাক এপ্লিকেশনে একসেপ্ট হয় মোৰতে যেটো আইএসআৰ ব্ৰ্যান্ড ভ্যালুটো ফৰ ৰিসাৰ্চ এটো মানে যথেষ্ট ভাল হৈ গৈছে এতিয়া আৰু ইয়াত আহি পেলাই কৰিবলৈ আমাৰ কেইবাটাও প্ৰগ্ৰাম আছে যোৱা 2 বছৰ হোৱা নাই এনে ইয়াত সামাৰ ফেলোশ্বিপ হয় তো সামাৰ ফেলোশ্বিপ ইজ ওপেন ফৰ অল তাৰপিছত যিমান ষ্টুডেন্ট আছে সিমান ষ্টুডেন্টে এপ্লাই কৰিব পাৰে তাৰপিছত কিন্তু ফিক্সড নাম্বাৰ অফ তাৰমানে হেৰি কাৰণ ইয়াত হোষ্টেলৰ ইছ্যু আছে তো আমি হোষ্টেলত ৰাখিব লাগিব হোষ্টেলত যিমানখিনি হোষ্টেল খালি থাকে সাধাৰণতে বিএসএম ষ্টুডেন্ট নাথাকে হোষ্টেলখিনি খালি থাকে বহুত ষ্টুডেন্ট লোৱা হয় সামাৰ ষ্টুডেন্টক আৰু তেতিয়া কি হয় ধৰা হাতি যেতিয়া এপ্লাই কৰে তেতিয়া হলে ইন্ডিকেট কৰিব লাগে যে কাৰ লগত কাম কৰিব খুজিছে তেনেকে ধৰা মোৰ নামতে যদি কোনবাই তেনেকুৱা ধৰণৰ ৰিসাৰ্চ কৰিব খুজিছে তেনেকুৱা 15টা 20টা ষ্টুডেন্ট থাকে সেইখিনি মোলে পঠাই দিয়া হয় তাৰপিছত তাৰ ভিতৰত মই তাহাঁতৰ সিবিটিভি চাই এনেকে হেৰি চাই পেলাই বা ক'ৰ পৰা আহিছে কি কৰিছে চাই পেলাই তেনেকে 3জন বা 4জনৰ নাম মই দিলে তেওঁলোক আহি পেলাই ইয়াত কৰেহি এই প্ৰসেসটো আছে এই প্ৰসেসটো ইটস লিমিটেড এনেওতো বাকিবিলাক ষ্টুডেন্টে ক্লাছৰ সময়ত আহিব নোৱাৰে সাধাৰণতে সামাৰতে আহে গতিকে সামাৰত as far as the hostel accommodation is possible students can come they should apply for the process আৰু যেনেকে মই যদি কাৰবাক জানো অলৰেডি যে বহুত ইন্টাৰেস্টেড তেনেকে বহুতে ইমেইল কৰে তেতিয়া হলে যেতিয়া সেই নামবিলাক আহে তেতিয়া হলে মই তেনেকে সিলেক্ট কৰিব পাৰো
ওকে থ্যাংক ইউ মই অসমৰ ষ্টুডেন্ট খিনিকো আহ্বান কৰিছো যে বিএসসি কৰি থকা সময়ত এনেকে ৰিসাৰ্চৰ কাৰণে ইন্টাৰ্নশিপৰ কাৰণে যাতে সুবিধাবোৰ লয় উজ্জ্বল দাই কোৱা নিচিনাকে বহুতে নাজানিব পাৰে এইবিলাক কথা গতিকে আমাৰ প্লেটফৰ্মৰ উদ্দেশ্য এটা এইটো যে ষ্টুডেন্ট খিনিক এৱাৰনেছ পঢ়োৱা আৰু হেতু কাৰণে মানে আহ্বান জনোৱা সো ষ্টুডেন্ট খিনিৰ কাৰণে এটো আহ্বান থাকিল তেওঁলোকে যাতে এপ্লাই কৰে
সব আইসাৰতে আছে মোৰতে আইআইটিটো আছে মই এক্সাক্ট শিওৰ নহয় কিন্তু সব আইসাৰতে আছে এটো আমাৰ ইনফেক্ট মোৰ লাগে যে অসমীয়া ষ্টুডেন্ট বহুত কম আহে আৰু তেতিয়া দেখি বেয়া লাগে আৰু আহিলে মানে মইটো মানে ইয়াত কাৰণ এতিয়া ইমান কম আছে মই হেতক কেতিয়াবা কওঁ যে মানে ঘৰৰ মানুহৰ নিচিনাকে থাকিব পাৰে আৰু মই মানে সবকে যে মানে হেৰি কৰি ৰিকুৱেষ্ট কৰিছো যে তোমালোকে এপ্লাই কৰিবা at least এবাৰ আহি পেলাই চোৱা আহি পেলাই চাই I am sure that you will like it.
Thank you Ujjal da for your time and for your advice আৰু ইনফৰমেশন খিনিৰ কাৰণেও ষ্টুডেন্টৰ কাৰণে আমাৰ সময়ও শেষ হৈ আহিছে অলমোস্ট 2 ঘন্টা টাচ কৰো Thank you very much for this wonderful talk. Started, as Kalanda said, you started with basics and went to the most research-oriented part, and with the work that is going on inside your lab. So we were really interested to see that. Thank you very much for coming to our platform. So our next Haritu ase January 9th. Rifadda, just confirm this is the next session, or we don't have a session in the Christmas, right?
Hi. আকৌ মই উজ্জ্বলক আন্তৰিক ধন্যবাদ জনাইছো সকলোৰে হৈ বৰ ভাল লাগিলে আৰু আই থিংক ষ্টুডেণ্ট সকলো উপকৃত হ'ল আমাৰ নেক্সট সেশনটো একচুয়ালি জানুৱাৰী 9 তাৰিখে হ'ব আৰু গতিকে এই বছৰৰ আজি লাষ্ট সেশন হ'ল সকলোকে নতুন বছৰৰ শুভেচ্ছা জনালো আমাৰ তৰফৰ পৰা আৰু একচুয়ালি জানুৱাৰী অহা বছৰৰ প্ৰথম সেশনটো হ'ব জানুৱাৰী 9 তাৰিখে সো আমি এখন অনলাইন কুইজ পাতিবলৈ মনস্থ কৰিছো সো গতিকে কুইজ মাষ্টাৰ হ'ব সকলোৱে বহুতে চিনি পাই চাগে গুৱাহাটীৰ আশুতোষ দাস তেখেতে যথেষ্ট কুইজ কৰি থাকে সেই অনলাইন কুইজখনৰ ডিটেইলছ সকলোকে জনোৱা হ'ব বিশেষকৈ এডুকেশনালি কুইজ হ'ব বা সায়েন্স আৰু হিউম্যানিটিজৰ ডিফাৰেন্ট সাবজেক্টস কভাৰ্ড হ'ব আৰু তাত এটা একচুয়ালি সিঙ্গল পাৰ্টিসিপেন্ট থাকিব গ্ৰুপ নাথাকিব যেহেতু ইট ইজ এন অনলাইন কুইজ সো গতিকে এটা প্ৰিলিমিনাৰী ৰাউণ্ড হ'ব আৰু এটা ফাইনেল ৰাউণ্ড হ'ব গতিকে ডিটেইলছ আমি জনাম আৰু তাত কেশ এৱাৰ্ডো থাকিব সো সকলোকে পাৰ্টিসিপেট কৰিবলৈ অনুৰোধ জনালো আৰু ডিটেইলছৰ কাৰণে আমি ফেসবুক বা হোৱাটসএপ গ্ৰুপ বিলাকত ইনফৰমেশন দিম আৰু হদৌ শেষত আকৌ আজি নগাঁও কলেজৰ ষ্টুডেন্টস আৰু শিক্ষক শিক্ষয়িত্ৰী যিসকল উপস্থিত থাকিলে তেওঁলোকলৈ ধন্যবাদ জনাইছো আৰু লগতে আজি ডিআৰ কলেজৰো শিক্ষক আৰু ছাত্ৰসকল উপস্থিত আছে তেওঁলোকলৈও বিশেষ ধন্যবাদ জনাইছো আৰু আন যি ইনষ্টিটিউট বা কলেজৰ ছাত্ৰ ছাত্ৰী শিক্ষক শিক্ষয়িত্ৰীসকল আজি যোগদান কৰিলে তেওঁলোকলৈ আন্তৰিক ধন্যবাদ জনালো বিশেষকৈ এইখিনিতে যদি অনন্ত গগৈ যদি তেখেত আছে তেখেতক বিশেষ ধন্যবাদ জনাব খুজিছো তেখেত সহযোগ কৰি আৰু ধন্যবাদ আকৌ উজ্জ্বল আশা কৰো
ধন্যবাদ মোৰ খুব ভাল লাগিলে আহি পেলাই সকলোকে লগ পালো ষ্টুডেন্ট বিলাককো লগ পালো থ্যাংক ইউ ভেৰি মাচ ফৰ দ্য ইনভাইটেশন
ধন্যবাদ ভাল লাগিল
Thank you. We kindly request the participants to kindly log out, please.